Hi and welcome to Prototype. We will be solving the problem for LeetCode 235, lowest common ancestor of a binary search tree. This is another problem in the LeetCode 75 study plan. Let's get to it. So given a binary search tree BST, find the lowest common ancestor LCA, node of two given nodes in the BST. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in the tree T that has both P and Q as descendants. And they also allow a node to be a descendant of itself. Okay, and so we're given an example with the tree with the root node 6 having children 2 and 8, with child 2 having children 0 and 4, and with child 4 having children 3 and 5, and with child 8 having children 7 and 9. And if we're given P equal 2 and Q equal to 8, so 2 and 8, then it wants us to return 6, the root node. And in this case, there's only one ancestor, but let's just look at some other potential examples with this particular tree. So if we were given P0 and Q9, then the lowest common ancestor, again, there's only one, it would be the root node, right? It couldn't be 2 and it couldn't be 8 because 2 and 8 are not ancestors of both 0 and 9. Now, if we were given 3 and 5, 3 and 5 have 3 ancestors, 4, 2, and 6, but it wants us to return 4 because it's the lowest common ancestor, or if it's easier for you to think of this way, the closest ancestor to 3 and 5. Okay, so the trick in this question is to leverage the fact that this is a binary search tree, and in a binary search tree, every child to the left of the node must be smaller than the current node's value, and every node on the right side, or the whole subtree on the right side, has to be larger than the current node as well. And both the left subtree and the right subtree must also be binary search trees. Okay, there's a couple other things that we should keep in mind. So all node values are unique. P will not equal to Q, and both P and Q are guaranteed to exist in the binary search tree, so things to keep in mind as well. All right, let's do a recursive solution first. So let's create another function. Let's call it recursive. It's going to take a node, and it's going to take P and Q. And so, again, the fact that this is a binary search tree means that everything to the left of the current node, so every child on the left is going to be smaller, and every child on the right will be larger. Okay. How do we find the closest or lowest common ancestor? Well, let's think about it without just looking at the problem. Okay, we're given the root nodes, we're given 6. Again, let's say that we're given P3 and Q5. Well, both 3 and 5, how do they relate to the current node or the root node 6? Both 3 and 5 are smaller than 6. What does that mean? That means that both 3 and 5 are on the left side of 6. They exist in the left subtree of 6. And because both values exist in the left subtree, there must exist some other node that would be closer to the children 3 and 5, right? So if both of the values P and Q are smaller than 6, then we traverse the binary search tree to the left, and then we can compare the next node again with P and Q. All right. The child node of 6 is 2. How does 3 and 5 compare to 2? Well, both 3 and 5 are larger than 2, and therefore they must exist in the right subtree of 2, and therefore there must exist a closer or a lower ancestor to 3 and 5. So because 3 and 5 are both larger than 2, we traverse again to the right child. Finally, we get to 4, and we compare 3 and 5 to 4. 3 is smaller than 4, and 5 is larger than 4. And in fact, this means that 4 must be the closest ancestor or the lowest common ancestor to P3 and Q5. Okay, let's think of, let's say 5 and 7. Okay, just one more example here, 5 and 7. 5 is less than 6, so it exists on the left subtree. And 7 is greater than 6, so it exists in the right subtree. Again, because both children exist in different subtrees, so again, a 5 in the left subtree and 7 in the right subtree, there cannot be any lower or closer ancestors. 6 is the closest ancestor. So that's what we're going to leverage. Okay, let's get to it. So if the node value is, let's compare P. So if the value of P is less than the current node's value, and Q's value is less than the node's value, then what are we doing? We're going to traverse to the left. So call node.left, and then we just pass through P and Q. And we'll return that. Otherwise, if P.value is greater than node.value and Q.value is greater than node.value, then we will traverse to the right. And again, pass through P and Q. Otherwise, we must be at the lowest common ancestor, so we return the current node. And finally, we can just return recursive, and we call recursive on the root P and Q. All right, let's run it and submit. Okay, so beats 45.58%. And just as a check, let's just submit one more time, see if it can be any better. 99.5%. There you go. That's LeetCode. From 45 to 99. Okay, so now we can leverage something very similar to do this iteratively. And why don't we just do that? So let's get rid of this. Get rid of this. And iteratively, let's use a trusty while loop. Okay, we'll need a variable for the current node that we're at. And here we can just say, well, the current node is not null. And then otherwise, we're going to be doing more or less this exact same thing. So if the Q value and the P value is less than the current node's value, what are we doing? We're going to traverse to the left. So cur is going to be assigned, cur.left is going to be assigned to cur. And then similarly on the right side, cur.right will be assigned to cur. Okay. And to save some space, we can just say else we return the node, because again, if both values P and Q are smaller than the current node, then we traverse left. If both values are larger than the current node, then we traverse right. Otherwise, we have found the closest ancestor. Now, this is the most concise way to write this. I probably wouldn't write this in production. But this does work because, and we don't even need to say return cur here because we know that there will always be an answer. But otherwise, I would probably say wrap this and wrap this in the Boolean expression, right? And then once neither of these are passed, then we know that we can break out of the loop and return cur. But anyway, this is more concise. So let's go with that. Submit. Okay, 90.2%. Okay, So that is the recursive and iterative solution to LeetCode 235, lowest common ancestor of a binary search tree. Subscribe to see more. We'll be following up with the rest of the LeetCode 75 study plan questions in short order. Thank you and see you next time.